So, chapter 2 in your book deals with the idea of logical reasoning. I said back at the beginning of the year that in geometry, we're going to look at how shapes work, but we're also going to learn how to think through things and explain why they're true. And it's that second thing that we're going to be looking at in chapter 2. Now, I will be honest and tell you, for a lot of people, this is honestly their least favorite part of geometry, but that doesn't mean we don't have to do it, and it doesn't mean that you can't do perfectly well with it, which is what we're going to see that you do right now. In the chapter, we're going to learn two different kinds of reasoning. Today, we're going to end up talking about the first one just real quickly. You'll be doing some problems with that tomorrow. And then later on, we'll move on and talk about the second of the types of logical reasoning. First kind is what's called inductive reasoning. And inductive reasoning, the idea is that you look at things and you try to observe patterns in what you see. So for example, there's a couple of patterns that you can see in the pictures that are on the screen. There is one where you see a triangle and then a square and then a pentagon. And when I was going through this in class this afternoon, I asked people, okay, so what's got to come next? And I had one person that pretty much immediately raised their hand and said 6 sides. And I said, so do you know what a 6-sided shape is called? And eventually they came up with hexagon, which is right. And that would be a very reasonable answer. It looks like they're adding a side each time. So we would have a hexagon and then a heptagon with 7 sides and an octagon and a nonagon and so forth. You'd keep adding one side each time. Now that certainly is probably the most reasonable explanation for what would come next, but it's not necessarily the only thing that could happen. They could, for example, keep alternating triangle, square, pentagon, triangle, square, pentagon, triangle, square, pentagon. And that would be a very reasonable possibility as well. And because there can sometimes be more than one possibility, that's why you don't always have an absolute answer when you have inductive reasoning. Now, there's another picture I have up here that I was asking people if they could predict what came next, and I believe it was Jacob Learer that almost immediately told me it has to be D that comes next. And what he was noticing was that the outside of the square was alternating white, gray, black, white, gray, and so he figured out it had to be the one that was black that came after that. It's also true that there are 2 black diamonds and then 2 sort of medium gray diamonds, and then you get 2 lighter colored diamonds. So the diamond and the square are both changing in a different pattern. But yeah, D probably is the best choice for what comes next on this one. The basic idea when you have inductive reasoning is you do look at specific examples like the shapes we were just looking at, and you recognize patterns which you're going to assume continue. You're going to use those examples to find a general rule. Now, I will tell you, you know that if you were actually in class, you'd very likely be taking down notes for these. And something you might want to do is to pause the video and actually jot down some of the notes before you race ahead to the next screen. The conclusion you make, the general rule that you try and come up with, we typically call a conjecture. So like that one that said the next shape has to have 6 sides, that would be a conjecture. A conjecture basically just means an educated guess. And it's not necessarily absolutely true, but usually it's good enough. And in fact, we use inductive reasoning all the time in everyday life. I was telling them in class this afternoon that my senior Math 5 class is also studying logic at the moment. And last week, since several of those guys are among our senior football players, I was telling them, now you could look back at what's happened every other time you've played Brit, And I bet you could predict that they're going to run the ball almost every play in their game this year. And gee, what happened? They ran the ball in almost every play this year. That's because you're observing what you've seen other games you've played and what you've seen on film, and you're predicting that that pattern is going to continue. Conjectures like that often are correct, and they do tend to help us get on the right track and make predictions like how to prepare for a football game, but they aren't necessarily always true. And the problem is that you find conjectures by assuming a pattern's going to continue, and you can't necessarily say for sure that patterns are always going to continue the way they did. You very likely may have seen before what happens when you assume that what you're going to do is make an ass out of you and me, and that, of course, is not something that necessarily you want to have happen. So there's one other term that comes up here, which is what's called a counterexample. A counterexample is one single example that shows that your general rule doesn't always work. Even though you might have a rule that's true most of the time, if you can find one situation where it doesn't work, that's a counterexample, and it shows the rule isn't always true. For instance, something that I could say is mostly true at Gurrigan is that we have Mass on Wednesdays. However, this week is a counterexample because since it's homecoming week, Mass is actually on Friday rather than Wednesday, so we don't have Mass on Wednesday this week. And there are some other times that happens, like when it gets to be Immaculate Conception, that'll be on a different day of the week because it's a holy day. But a counterexample is just one single example that shows that that rule is not always true. Here's one where it says that 2 is a counterexample to the rule that all prime numbers are odd, and that's because 2 is the one and only prime number that is even. I have one here that says, what could be a counterexample to they always cancel school when it snows? And there could be a lot of things that might be different. Like, for instance, maybe the snow started after school was already started and it came so fast they couldn't cancel it. In class today, I was talking about one time years ago, back when St. Joe School was still open. And we actually had snow that came during the school day on a Friday. And those kids down at St. Joe had to stay in the school all weekend long because they were snowed in down there. Well, that was a time when it snowed, but they didn't cancel because they basically couldn't. Another thing that could be happening is I never told you where it was snowing. Maybe it was snowing somewhere else, but not where our school is. Or like maybe it was Christmas vacation and they didn't cancel because there was no school anyway. All of those would be counterexamples to the original statement. Unless you can find an example that's true every single time, you can't prove that a conjecture is true using inductive reasoning. But a lot of times it's good enough. It works for everything you need to have it work for. So again, inductive reasoning, you use general examples to come up with, use specific examples to come up with a general rule. A conjecture is your educated guess on what you think is going on, and a counterexample is one example that shows this isn't always true. So that's inductive reasoning. Again, you'll have an assignment over that tomorrow, and probably about Thursday, we'll learn about other types of reasoning.